It is easy to think of the internet as an invisible, weightless cloud of data hovering somewhere above our heads. But in reality, the internet is a physical machine, the largest and most complex ever built. It has real weight, geographical borders, and hard physical limits. It connects billions of individuals, massive institutional databases, and a growing swarm of edge devices, all transmitting simultaneously. To understand how modern digital commerce functions, we have to look past the website interface and deconstruct the specific layers that make this transmission possible. This requires splitting the internet into two distinct architectures: the logical rules governing the software and the tangible hardware cables carrying the signal. Building a resilient digital business means navigating both the strict logic of those software protocols and the inescapable bottlenecks of the physical wires. At the primary level of internet communication, data is never sent as a single continuous stream. It travels in discrete units called packets. Through packet switching, large files are sliced into standardized packets. Each navigates an independent pathway through the network. To organize these scattered packets, the system relies on the TCP/IP stack, dividing communication into network, internet, transport, and application layers. Within that stack, the Transmission Control Protocol, or TCP, handles the complexity of assembly. It sequences the packets before transmission and guarantees they are stitched back together in the exact right order at the destination. The Internet Protocol acts as the addressing system, providing numeric addresses to route packets. Originally using 32-bit IPv4 addresses, capping at 4 billion devices, the network migrated to a 128-bit IPv6 format, expanding available addresses to over 1 quadrillion for mobile devices. Because humans are not optimized for memorizing massive strings of numbers, the Domain Name System, or DNS, was built as a translator. It converts those numeric IP addresses into the readable, natural language URLs you type into your browser. This logical layer provides perfect organization for data traffic. But a routing rulebook cannot move a single byte of information without a massive physical medium to travel across. That medium is the geographical, tangible network that spans the planet. The global backbone of this machine is owned by Tier 1 internet service providers. These are the telecommunications companies that process the highest volume of international traffic. This Tier 1 backbone relies on transoceanic fiber optic cables resting on the ocean floor, connecting continents and transmitting data via light pulses at unprecedented speeds. Branching off that central spine are Tier 2 networks. These regional connectors do not own the global lines. Instead, they lease transit access from the major Tier 1 providers to link regional networks together. Finally, the signal reaches Tier 3 networks. These are the local providers that supply the last mile of broadband, DSL, or cable access directly to the end user. Every millisecond of delay during checkout is dictated by the exact distance packets must travel and specific bottlenecks along this multi-tiered physical highway. The World Wide Web is distinct from the internet. It is a specific service built on top of those physical layers. The web operates on a client-server model. Your personal computer, acting as the client, sends a request across the network to a high-powered server, whose function is to store files and serve the requested information back to you. To find that specific content, the web relies on the Hypertext Transfer Protocol, or HTTP, to locate the resource, while markup languages like HTML and XML format exactly how that text and data appear on your screen. Over the last decade, this model evolved into cloud computing, a centralization where computing power and software are accessed entirely over the internet rather than being stored on a local hard drive. The cloud you see here is composed of endless rows of physical server racks in massive data centers, offering 3 distinct tiers of utility: infrastructure as a service, software as a service, and platform as a service. By utilizing public, private, or hybrid clouds, companies offload the enormous capital expense of buying hardware and maintaining localized IT departments. This architectural shift allowed a startup with 5 employees to rent the exact same enterprise-grade computing power as a multinational corporation, leveling the playing field for digital commerce. But server farms are only half of the equation. To see where the network is actually growing, we have to look at the edge, the devices sitting in the hands of consumers. The sudden introduction of the smartphone rapidly fractured the traditional computing model. Users were no longer tethered to desktop PCs with hardwired connections. Mobile operating systems enabled situational, on-the-go access from anywhere on the planet. These edge devices rely on local wireless protocols to function, bouncing signals through Wi-Fi routers using 802.11 standards or connecting to peripherals via Bluetooth. When Wi-Fi is unavailable, they default to telephone-based wireless networks. As infrastructure upgrades to 5G, it unlocks the bandwidth required to run complex, data-heavy applications instantly. An e-commerce strategy is incomplete if it does not account for the high-bandwidth, volatile nature of mobile edge computing. When you assemble these pieces, the true shape of the network reveals itself: a bedrock of TCP/IP routing rules, a physical layer of global cables, centralized cloud servers, and a sprawling canopy of mobile devices. Every time a customer clicks buy, a packet-switched pulse shoots down from the mobile edge, navigates the logical protocols, races across the ocean floor to a designated server, and returns the confirmation in a fraction of a second. The demands on this system are accelerating. The next iteration of edge computing utilizes natural language processing, relying on conversational AI and intelligent digital assistants to handle complex scheduling and routing. Simultaneously, augmented and virtual reality applications attempt to overlay immersive worlds over our physical space, requiring continuous, massive data streams to maintain the experience. As the digital economy pivots toward these resource-intensive interfaces, the ability to scale depends entirely on a technical mastery of the underlying network infrastructure.